Okay, so we're actually going to talk about acceleration again, but how it applies to gravity. So gravity is basically a force that when we're near the Earth's surface, so this is not just Earth, but any other masses in the universe have its own gravitational force. So Earth has its own gravitational force, and we're just going to focus on that. If we ignore the effects of air resistance, so our atmosphere has molecules of air, and if we are flying through the air quickly, even though we don't see it or feel it, those air molecules are working against us, and that's what we call air resistance. So the acceleration of falling objects, so if something were to be falling near the Earth's surface, measurements show that gravity actually has a force that causes an acceleration of 9.8 meters per second squared. So this is our gravitational constant for Earth when we are near the Earth's surface. Okay, and so two things can happen when we're falling, and I'm just going to deal with one at a time here. So acceleration due to gravity, scientists have measured a constant of approximately 9.8 meters per second squared. Depending on where it is you're looking on the internet or in different textbooks, it might vary a little bit. And in fact, a lot of textbooks just round it to 10 meters per second squared. So what that means, if we were to break that down, remember that that meters per second squared is the same thing as saying meters per second per second. So if we said 9.8 meters per second, what that actually means is that the acceleration due to gravity says that for a falling object, it is increasing its speed by 9.8 meters per second every second it falls. So every second something falls toward the Earth's surface, it's increasing by 9.8 meters per second. So its velocity is increasing by 9.8 meters per second. Okay, so two things happen when we're falling near the Earth's surface. One thing is free fall. If we ignore the effects of air resistance, if we didn't have an atmosphere that we were falling through and air molecules that were working against us, we would have something called free fall. And that is the acceleration. We would just continue to accelerate at 9.8 meters per second every single second until a certain speed was reached, or you hit the Earth's surface and most likely die. Something else happens though. So we'll use a parachuter or a skydiver as an example. For the first little bit, when they jump out, they are in free fall for a certain amount of time, meaning that their velocity is increasing by 9.8 meters per second every second. So they're speeding up their speed or accelerating. But because we have air resistance surrounding Earth, which is that atmosphere of air molecules, what starts to happen is those air molecules are working in the opposite direction. So we have air, and because this person's falling in this direction, we have air molecules that this person's trying to work its way through. Even though we don't see them and we don't necessarily visualize them as being there, it's working against any object that's falling. And what happens after a certain period of time is that resistance or drag force of the air eventually balances out or equals the effects of gravity. And we call that terminal velocity. So terminal velocity is when the force of air resistance is equal or balanced to the force of gravity. And basically what happens is you stop accelerating in your fall. You would just fall at a constant speed. You reach a certain speed and you just continue to fall at that speed. Okay, and that's what we call terminal velocity. Okay, so that's it for the note. Just a few interesting tidbits of information. So let's look at some things maybe you can relate to when we think about gravity. Anyone's been to Canada's Wonderland, we have the ride called the Drop Zone. So just to give you some facts about the Drop Zone, that we, when we ride that, and I've done it once, not really into that sort of thing anymore. I used to love rides like this. So for 3 seconds, of this ride on the Drop Zone, you are experiencing free fall. So what that means is for 3 seconds of this drop, you're increasing your speed or you're accelerating. And then then the machine kicks in and starts to slow you down so that you don't end up injured or dead. Another interesting piece of information. So if we know, just to kind of give you a background, some of you have probably heard of something called a G-force. Well, that G actually stands for gravity. So we know that just the acceleration due to gravity is 9.8 meters per second based on what scientists have measured, squared. So when they talk about G-forces, what that means is if we know this is just the regular acceleration due to gravity, they call that 1G. So 1G is equivalent to just the regular acceleration due to gravity. So when you hear things traveling at 2 and 3 Gs, we're just basically multiplying this number by that amount. So if it's 3 Gs, it's 3 times 9.8 meters per second. And so it's a greater force that's acting. And the interesting piece of information that I have for this is if we think about astronauts. Okay, and if we think about astronauts, I'm going to get rid of this for a second. I'm just going to give you a tidbit of information first that tells us what humans can withstand, because obviously we're not designed, our bodies are not designed to withstand a certain amount of gravitational force or forces on our bodies, because we have organs, we have blood flowing through our body that could all be affected by this. So just interesting piece of information. We as humans can withstand, so humans can take or can handle, let's say that our bodies can handle up to 30 Gs for about half a second. Now to put into perspective what an astronaut goes through, when an astronaut is taking off, when astronauts are taking off, during takeoff, they can experience up to 10 Gs for several seconds. Now think about what effect that might have on their bodies, their blood flow, their organs. And so basically what they're saying is that at this acceleration, if the astronauts were standing, and this is why they don't stand during takeoff, they would faint because of the loss of blood to the head. So think about if your body's moving at 10 Gs, so is everything inside. So the blood's going to rush downward just like that same force on your body. And so that's why they've got to be certain positions during takeoff so they can avoid the negative effects of this G-force.